Good evening, minions. It's nice to be here. My name's Nathan, uh, and I am a PhD student in chemistry. I'm hopefully a few months away from graduating, and I'm a great big nerd, and I really like talking about chemistry, and it's fun. So I come on here and I just do some chemistry stuff, and then I talk through what I'm doing. Well, I work through some problem sets, and I just talk about my approach, talk about some of the theory that underpins it. And yeah, it's sorry, I'm just distracted by the music. That's just it's a strange song that had a Pokemon sound effect, and I'm terribly distracted by this. Also, hey, look at my very pretty nails. I'm feeling very good about it today. Finally had some time to work on them yesterday, and then went to a very nerdy trivia put on by a couple of my friends. It was very, very fun. Yeah, aside from that, I don't think I've got anything particular on my mind that I would like to talk about. So I think what we're gonna do is we'll just hop into doing some chemistry problems. So today I'm going to be focusing on SN1 and SN2. Stands for nucleophilic substitution. Don't worry about the 1 and 2 right now. We'll get there. Yeah. So let's head over here. That is the entirely wrong screen. Very good. Okay. So starting out with drawing Lewis structures for doing the reactions, because the SN1 and SN2, the substitution reactions, there's a few key points about them that make it really important to have a good understanding of what the mechanism of the reaction is. So we have to go through a specific order of operations, and the order that we do things in and the orientation that we have things in is important, because SN1 and SN2 have specific outcomes in terms of their stereochemistries, like which groups are pointing where on the molecule before and after. And so we'll talk about those as we get to them. I'm just grabbing a couple things from my model kit. There's a very helpful viewer last week that told me about this kind of like virtual model kit program, this IBOView. And so I downloaded it tonight, but it is not entirely intuitive, so I do not have it working well enough at the moment, so I'm just going to do as best as I can with the physical model kit and my incomparable artistic skills. So we'll get into drawing some Lewis structures. Hello, my love. Hi. Ba-dum-bum-bum. Oh man. Oh. I have no kittens with me today. I am doing this solo, which makes me terribly nervous. They're really very helpful. So, drawing Lewis structures of these various things. Acetic acid. So it gives the kind of like condensed structural formulas here. So we can just build up molecules based on that. So we've got, starts with a methyl group, and so we've got, going to put H3C here. So I don't really, the way they've got this written is, well, it's actually okay, and I'll tell you why. So when we're going along a condensed structural formula like this, I'll just draw this out a little bigger so I've got some room to talk about it. Okay. So when we are going from a structural formula to a Lewis structure, so we just basically what we do is we start on the left and then we just go to the right sequentially, which seems like I'm saying something really obvious, but there is nuance to this that's going to matter. So when we start, so we start on the left, so we start with just drawing a carbon. That's going to be our first molecule, and then we'll draw this H3, but we do this one atom at a time. So you've got your carbon, so the next atom that you should draw is a hydrogen. And now there are 3 of these, so we have to keep drawing hydrogens. And in order to do that, so we're not going to draw it from this hydrogen to another one, because that would be really strange, because hydrogen can't support 2 single bonds. And so, yeah, the hydrogen can only have 1 bond to it. And so that one has already been made from this carbon. So we can't attach anything to the hydrogen, which means that, so we've gotten to the second set of atoms here, to the hydrogens, but we can't go any further, so we have to go back to the initial carbon and attach another hydrogen there. And then we have to do that again to get all 3 of our hydrogens out, and all of these must be attached to that first carbon. So now that we've got that first carbon's done, the hydrogens are done, now we can move on to the next atom is another carbon. Now, with what we've drawn so far, this CH3, there is nowhere else that we could put it except attached to the carbon, because we can't attach it to any of these hydrogens. So we've got exactly one choice here. Carbon should always have 4 bonds to it, be they single, double, or triple bonds, but they must have 4 bonds. And if it has more or less, you should go back and try it again. So we've gotten this carbon is dealt with. Now we have to move on to the next atom, which is going to be an oxygen. And so we're going to put an oxygen here. And there's a couple ways you can draw it, but we'll go with what they've got drawn for now, and then I'll show you a couple others after. Or maybe I won't. We'll see. So we've got a bond from the carbon to the oxygen here. Now we could technically draw, because we have to have 2 oxygens here. So we could draw a second bond from this oxygen and connect to another oxygen. Because oxygen supports 2 bonds. It is happiest with 2 bonds and 2 lone pairs. But this presents a couple of problems. One problem is that this has created a peroxide. It is just a compound that has an oxygen-oxygen bond in it, specifically an oxygen-oxygen single bond. Because if it had a double bond, it would just be, like elemental oxygen. It's another thing entirely. But a peroxide is incredibly reactive functional group. Like it's a very strong oxidizer. You see it in things like hydrogen peroxide, which is H2O2. So cue all those all those corny jokes about chemists walking into a bar or ordering H2O2 and they die. Yeah, because they drank hydrogen peroxide. So this has an oxygen-oxygen bond in it. Forgive my drawing. Told you I'm really, really good at this. So this has that oxygen-oxygen single bond, which is terribly unstable. It will be very happy to use these electrons to attack something else, because this doesn't like to exist. and things that don't like to exist are very reactive. So this is something that you can do this. But the first problem here is that you've made something extremely reactive. And that's not again, like, you could do this, but there's a second problem that is actually significantly bigger, which is that when you do this, and if we carried this all through to the end, we'd put a hydrogen on the end of these oxygens, and that would satisfy all of the atoms that we've got in this compound. However, the problem is right here, because this carbon has 2 bonds, and that is not enough. That is if my years of study are not failing me, that is less than 4 bonds. So this would be an extremely unhappy carbon with, I don't know why I wrote 2 there, with multiple positive charges. It would be missing about 4 electrons around it. Just an extremely unhappy thing, and breaks the rules of making a good Lewis structure. So we have to do it a different way, and I'm going to erase all these. Okay. So the other thing that we can do is, instead of attaching the second oxygen to the first one, we go back one more atom and we attach it to the carbon. So now this is so far kind of okay. We're not done yet because we have to attach a hydrogen here. Now we have got 3 options, three potential candidates where this hydrogen could go. It could go on the carbon. It could go on one of the oxygens, or it could go on the other oxygen, which is technically the same choice, but don't worry about it too much. So let's take this case by case. If we, if we attach it to the carbon, now the carbon has 4 bonds to it, and it's happy, but we have now 2 oxygens, which, well, they would have a bunch of electrons around them. I've actually got too many here technically, but don't worry about it too much. But the point is, for this Lewis structure that we've been told the structural formula to, it is a neutral compound, and we can't have these charge groups there because all the oxygen should have 2 bonds to them. So we have to go back again and do this a little different. Okay, so we're not going to attach the hydrogen to that carbon. We're going to put it onto one of the oxygens instead. And this is almost done. So now this oxygen's happy. This oxygen needs 1 more bond, and this carbon needs 1 more bond. But we are out of atoms. So the next thing that we can do is, if we count up the number of total valence electrons in this molecule, then we can kind of see where we've got some leeway to put other electrons around. So we've got 2 carbons, and carbons have 4 valence electrons. So it's 4 times 2, because there's 2 of them. Hydrogens have 1 valence electron times, and there are 4 of them total. And then oxygens have 6 valence electrons, and there are 2 of those. So it's 8, 4, and 12. So this makes about 24 electrons in total. And so when we're counting these up, bonds count for 2 electrons, because there's 2 electrons in each single bond. And then once we run out of electrons in single bonds, then we will populate the rest as lone pairs around whichever elements can handle those. So in terms of bonds, we've got 1, 2, 3, 4, 5, 6, and 7. So it takes care of 14 of our electrons, and we have 10 left. And now I have to move, so you can see this. There we go. Okay, so now I've put all these random dots out here, which are going to come back and bite me in the butt. So I need to take those out because it annoys me to have them there. Okay. So now we can. It is very reasonable to assume in these cases that this is a neutral molecule, and pretty good bet that the that each atom individually is going to be neutral. So we just have to fill its octet, and so for the oxygen that turns into 2 bonds and 4 valence electrons. And so when we're, that's valence electrons, good lord. Lone pairs is almost what I meant to say because I said 4. It has 2 lone pairs, which is 4 electrons. Yes, I promise I'm terribly good at this stuff. So that's going to be a neutral oxygen overall because a neutral oxygen has 2 bonds and 2 lone pairs. And then that takes care of 4 of our valence electrons, and then the rest we could put around this oxygen. But that, so that would be 10 electrons in total that we've added in the form of lone pairs, but we're not quite done because this carbon still has only 3 bonds around it, whereas this oxygen is also unhappy having 1 bond and 3 lone pairs. So this would prefer to be a double bond, which is what we would normally expect for an acetic acid, because this is now the carboxylic acid functional group. And so this uses all of our electrons and all of our atoms, and everybody's neutral, so we're pretty happy with that. Okay, so I have been over drawing Lewis structures of various compounds before, so I'm not going to belabor this, but we can just draw out these structures. So acetic acid, this, oxygen, okay. So that's our acetic acid, acetaldehyde. The other thing that we could do, like, I think my inclination is to draw out all of the atoms right now, because I think in mechanisms, it's easiest to start out with drawing out all of the atoms explicitly, at least around the reactive sites, because it's just it's too easy to just lose atoms when you're drawing out line structures like this one. Like it's very easy to forget that there's there's hydrogens attached to those implicit carbons as well, and it can be also very easy to just like miscount the number of carbons in a chain. So it's always a decent idea to like draw the atoms out fully, and if it helps to number your carbons, by all means do it. I think that is a really good way to stay on track. Yeah, sneaky little dudes indeed. Cheesy as a case, it's lovely to see you. Welcome, welcome. I hope you've had a good week. And happy Friday. Yeah, so alright, so acetaldehyde. My week's been okay. Yeah, it's been busy. It's been a lot, but it's been an all right week, and got some productivity done. That is a really weird way to say that, but it's already out there, so I'm sticking with it. Okay, so acetaldehyde. CO, and then H. And then we fill out our oxygens with lone pairs and all this stuff. So, are there any interesting ones to draw out? Acrolein. That one's actually not too bad. We can do that. So this one looks like. So this one is very kindly specifies that there's a double bond between these first two carbons. Also about last stream, it turns out Franz Kafka, Wikipedia wasn't overly flattering to Kafka. I submitted up with a post about Kafka. Yeah, fair enough. I honestly, I know terribly little about Kafka, but yeah. Did we talk about Kafka last stream? I don't. For whatever reason, I have no recollection. I remember talking about Wikipedia, and but yeah, I know very little about him. All I've seen, I saw a sculpture of well, not a sculpture, like an art installation that was depicting Kafka. It was in Prague, all those little rotating metal bits, and it was really cool. It was quite neat. Okay, acrolein, right. So yeah, double bond between the first two carbons, and then this one is connected to a hydrogen, and then we can't go any further with that, so we go back to the carbon and make another carbon, and then a carbonyl and a hydrogen. My drawing skills are doing so good today. We were talking about Wikipedia's accuracy. Oh, right. Gotcha. Kafka's reading too flattering. Yeah, fair enough. I'm kind of tempted to go read about it now and see how very unflattering it is. Yeah. I forget what I was going to say, so I'm just going to pretend I meant to do that. Is there anything? T-butyl isonitrile. I think I'm just going to take these off. Okay. All right. Okay. So I'm going to get talking now about these SN1 and SN2 reactions, because that I think is going to be the interesting bit for today. Now. This subject, and well, really all of any chemical reactions are. Let me start again, because I started without a I started the sentence without a plan. We need to try again. Like all of these reactions, all these mechanisms that we're going through, I like if at any point I say stuff that like doesn't really make sense or appears to refer to something I haven't explained, please let me know, because I'm very accustomed to talking about these reactions using kind of the language of molecular orbital theory, which is kind of the like it's just how we talk about these things. It is like the different orbitals around these atoms that electrons occupy. Now I'm not going to get into like a really like deep survey about like what molecular orbital theory is. Because that, I mean, people have written volumes about just molecular orbital theory, and it could be people teach entire courses on this stuff. So I'm going to probably end up referring to it sometimes, but the key about MO theory is the abbreviation for it, is that so electrons exist around the atoms that they're attached to in these things called orbitals. I do not for the life of me know when this gets introduced in high school chemistry, or if really, because I encountered it first in university, but basically electrons occupy orbitals around their atoms. Those are its home, and they're very happy in there. Now, every orbital has a capacity of exactly 2 electrons, and um, and reactions happen between orbitals that are filled and orbitals that are empty. And wait, why do they orbit? Orbitals is not a good name for them, unfortunately. So they're again. So they're not so you've probably seen like kind of the Bohr model of an atom from Dr. Niels Bohr, which just kind of has this it's called like the planetary kind of model of atoms. So it's got like the nucleus, and then it's got these different orbitals that the electrons occupy. And that's where the name comes from, because at the time they thought that this was the case, that electrons were these particles that just orbit the nucleus very, very fast, and they thought that they would orbit the nucleus in these kind of like spherical orbitals around, like these spherical orbits around the central nucleus. This was like a really big step in chemistry. It was very important at the time, and it was a revolution to our understanding of what atoms are. However, it's wrong. and a big part of the reason that it's wrong is because it assumes like a purely particle nature of electrons, but electrons have a wave particle duality to them, just like photons, just like light has wave and particle properties to it, because because the quantum world is a very, very strange place. So this model that gave us the misnomer orbitals was very important, but it's wrong. So Bohr model only correct when observed. It isn't correct at all. It is a straight up incorrect model, and yeah, the observed versus non-observed. Oh man, that's oh, that's a can of worms. Yeah, and we did already talk about that a few streams ago about the observer effect. So it's like whenever you measure an electron, you're doing so by hitting it with a photon and receiving that information. But because you hit it with a photon, now its nature has changed because of that interaction, and so it's no longer the thing that you think you see. It's weird, it's wild, it's wacky. But that's okay. Nature is under no obligation to make sense to us. So yes, this planetary, it absolutely is perplexing. It's it's weird stuff. And like one thing, oh man, yeah, if you want to annoy a chemist, just try saying that atoms are 99.99 whatever 9% empty space, because that is false. It is just a pure misunderstanding, which is actually largely based on the Bohr model that depicts this as mostly empty space. But when electrons are around a nucleus, these are not just these tiny little charged particles zipping around the nucleus, and like physically orbiting. That's not what it is. An electron exists in the orbitals that don't orbit as a standing wave. So it is pure. It exists as a wave function. And so is most science curricula academia based on the Bohr model? Nope, absolutely not. It gets introduced, but kind of as like, this is what kind of like this was part of the progression of our understanding of atomic theory, and so it's held up as like important on in that respect. Um, but yeah, exactly, team. It was a stepping stone, because like before this model, the Bohr model, there was I think it was Rutherford had like this plum pudding model, they called it, where you've got all these like embedded electrons around a nucleus, or yeah, and it's just it fit some experiments better than what they had at the time. So they adopted this plum pudding model where like everything's just kind of stuck in like little. And this is like how it was described. It was like raisins in a plum pudding. It's interesting language, but something that was accessible to people at the time. And so this plum pudding model evolved into this planetary model. But now both of those are recognized as like these are archaic. These are obsolete ways to think about atomic theory. So yeah, really is that like you may have heard that electrons exist as probability densities. And that's a correct way to think about it. But effectively, if you think about this as like there's it's the electrons in an orbital. So if we've got the nucleus here, and let's just say we've got so this is one that's called a p orbital, and so it has these two lobes of electron density that are exactly the same size and shape, despite what I've drawn here. And so there's different phases to the electron density in this orbital. There's a like you could call this like a plus phase and a minus phase. It's not talking about a charge. It's just talking about, this is a positive phase of the electron density. This is a negative phase of the electron density, not referring to the charge. But just like the yeah. So if that's the wave function of the electron in the positive region, then the negative region would look like that. Yeah, positive and negative as in position. Like if you graphed these two wave functions, like as just like a sine wave along a plane of coordinates, then you'd have let's just so yeah, you'd have these different like positive and negative. You'd have positive and negative portions of each, but they're just opposite to each other in phase. And so this is kind of what's happening here with the different phases of the orbitals. But yeah, so the constantly changing position, not exactly that they're changing position, just that like this space around the nucleus is like has this standing wave function of the electron, and so like it's like in a microwave. Your food gets bombarded with microwave radiation, and the inside of the microwave is shielded by this kind of like conductive net over it called a little Faraday cage, and that kind of like contains this radiation, and just like redirects it so that there's just this continuous like microwave radiation inside the microwave, kind of with just like different values along these sine curves at each point in the microwave and around the nucleus. So it could be called a duality. So this is part of the duality of electrons, is how I would describe it. Is this how electrons exist in orbitals? Is like the wave portion of their wave particle duality, and yeah. The opposite of these. What I said? Yeah, you could say that. Yeah, so like all of these orbitals have positive and negative portions of them, except for the s orbitals, which are just spherical around the nucleus. So those, at least, I have to think. I'm just trying to think if there's a negative component of a spherical orbital, but is that the same case of the Einstein equation where the universe had an expanding contracting term, there was an opposite force value term? No. So I don't think that's comparable here, because that was oh boy. Yeah, so that's when he was talking about his special relativity. And yeah, I don't think that this is the same thing. My understanding of quantum chemistry is tenuous at best. So I don't want to speak authoritatively on this. But I think that is a different kind of a thing. So the orbitals around atoms are these are solutions to what's called the Schrodinger equation, and so this just the Schrodinger equation, the solutions to them kind of set the shape of these orbitals and the size of the orbitals, and in those solutions to the Schrodinger equation, it comes out that one of these kind of lobes of electron density has this, arbitrarily assigned positive phase, and the other lobe has a negative phase, an opposite phase to that. The one with the cat, yeah, that same Schrodinger, despite kind of like making that Schrodinger's cat analogy to point out the absurdity of quantum physics, he did an incredibly great deal to advance our understanding of these kind of like wave particle dualities, and well, just our understanding of quantum physics and just how things operate at this level, and stuff gets weird. I was. So is this exact case with orbitals the cat analogy? No. So this is that is something else. So let me think, because that was right. So that was an analogy of just like the cat analogy was about the superposition of quantum states and how things like with these new like quantum computers, like you can have these qubits which are not just ones or zeros; they can be 1 and 0, and so it's a superposition of these wave functions, of these states, which can be described by wave functions that upon observation one of these will collapse and you'll be left with just one. And so it's just weird thing that like I super don't understand to any appreciable level. But so that was also a different subject than his solutions that describe atomic orbitals. Sorry for detours about understanding. No worries at all. You know me. I love my detours. I love my rabbit holes. Um, okay, so um, I'm I'm gonna redirect a little bit back to talking about just kind of the simpler view of orbitals, because like I don't understand a lot of the quantum chemistry that underpins it, and but we don't need to. Is the lovely news here. So, so what we need to know here is that electrons occupy these orbitals, and so like this here with these two lobes is one orbital, and in that one orbital there are two electrons, um, and so that's all that any orbital has like capacity for. You cannot fit a third one. You can't fit a third electron into an orbital. Now that being said, orbitals can be full. They can be occupied by electrons, or they can be empty. They still exist. Like these are still valid solutions to the Schrodinger equation, um, and but they can be empty, and chemical reactions only occur when you have a filled orbital interacting with an empty one. You can also have like partially filled orbitals, so orbitals with one electron interacting with another orbital with one electron. That can happen too, but that's not what we're going to get into today, because that stuff gets weird too. It's called radical chemistry, and yeah, it's complicated. Weird things can happen, and the mechanisms get very complicated. Um, but but again, like even like working out the mechanisms. So it's pretty specialized stuff. We don't need to do it to understand kind of what's going on with it. So for all our intents and purposes today, we will have filled orbitals and we'll have empty orbitals, and the overlap of those. Effectively, that is a chemical reaction. Okay. So, all right. Yeah, so that is going to come up a whole bunch when I explain what substitution reactions do. So does each electron just oscillate in a specific area? Yeah, pretty much. Yeah, that's a pretty good description of a standing wave. Hello, Daphne, my little love. How you doing? Hi, hi, hi. Like running side to side inside a box, but you're still in the box. There we're kind of getting back towards like a kind of like particle understanding of how these electrons are existing. Whereas like we have to think about it as like the entire box is taken up by the electron. If you're thinking about the orbital as a box, the electron is in the entire box. It takes up the whole box. It's like it just like creates a standing wave with the wave function of that electron that is just like going throughout this box. And those can be like when like those can be more diffuse. Like it can be like a larger box, and so the electron density of an orbital that's larger, or a box that's larger, like you still only got 2 electrons worth of electron density, and if you have those in a smaller space, your electron density is higher. But if you put them in a larger space, then they're more diffuse. So like it's kind of the way, like analogous to the way of like if you had a certain amount of gas, and you put it in a small container, it's going to be higher pressure. You put it in a larger container, it's going to be lower pressure. Similar to that. Yes, uranium would have much bigger boxes. because it has it has all these additional energy levels. Like as you go down a row in the periodic table, you add these layers of orbitals on top of each other. And yeah, so like the outer layers of uranium will start to be like very, very large orbitals with very low electron density around them. Yeah, yeah, it's a bit of a the bigger no. So I not it's not a case that the bigger the box, the more radioactive. Because radioactivity has to do exclusively with the stability of the nucleus, um, and that is it's a weird thing to do with like the proportion of protons and neutrons in a nucleus, and so like uh, because like nuclei are really weird because you have a lot of proton, like as you go down the table you have more and more protons packed into this very small area, and that's and like we talked about last time, you put you put two positive charges very close to each other, and they're not happy with that. They want to repel each other, they want to get far away from each other because of the electromagnetic repulsion between them. So if you do this with something like uranium, where you've got like 90 protons all in this small nucleus, all wanting to repel each other, but they're being held together by the nuclear by the nuclear forces. So there's like the four fundamental forces of nature are gravity, electromagnetism, nuclear strong force, and nuclear weak force. Yeah, it's a heck of a lot of protons, and this is why when if you can disrupt the nuclear strong force that's holding these together, I think it's the nuclear strong force. I want to look up more about that now. Yeah. That's ooh, squirrel. But yeah, so if you can disrupt this ratio of neutrons and protons to the point where now the electromagnetic repulsion of these protons rips the nucleus apart and forms these two separate nuclei with different numbers of neutrons and neutrons and protons. That's how you get radioactivity. So it's not that the bigger the nucleus, the more radioactive. It's that the less favorable the ratio of protons and neutrons, the more radioactive they get. The less stable your nucleus will be, and so on and so forth. So it's yeah, it gets to be a whole thing. But yeah, it's all based on this this balance of forces between the nuclear forces holding the nucleus together and the electromagnetic forces trying to rip it apart. Yeah, a little bit, but that's that's all right. That's how we learn. And for the record, like I absolutely I love all the questions that you ask, and you ask really good questions. And yeah, like I will never be I will never be upset that a question has been asked, because questions are amazing. And if like if 10% of my students would ask the number and the quality of questions that you do, I would just I'd be one happy boy. So yeah, like keep it up. I love questions. They're the best. You bet. Okay. All right. So after that little rabbit trail into how cool radioactivity is, and let me tell you, like I really enjoy talking about radioactivity. I don't know as much about it as I would like to, but yeah, I think it's very, very cool. been watching the development of fusion technology with profound interest. And yeah, at some point um, I will do some thorough reading, and we can definitely have a talk about just like what's going on with nuclear chemistry, because that stuff's really cool. I enjoy it a lot. One of the coolest presentations I gave in my undergrad. Um, yeah, no, it's fascinating, and it is made such incredible advancements in the last several years that it's just it's very cool. Yeah, one of the coolest presentations I ever gave in my undergrad um, was on like we were doing analytical chemistry, so we were talking about all these different ways of like the different methods of like isolating compounds from a mixture, which sounds like a really boring topic, and it certainly could be. But the one that I picked was a technique called liquid-liquid separation, which is used heavily in processing spent like nuclear fission waste, and got into some really cool some just some cool chemistry about how nuclear fuel is processed and stored, and yeah, and I got to like talk about like nuclear bombs and stuff on in a presentation, and it was just yeah, it was really neat. It was very cool. I turned something that was potentially very boring into I think a pretty good presentation. Oh my goodness, almost out of water already. Um, Absolutely, quite agree. Okay, so getting getting back around to nucleophilic substitution. Um, so yeah, it's a really important kind of like set of reactions, and it's pretty much always going to be taught in an organic chemistry course, because they're well super important, and like this is how things react. So talking about orbital overlap being kind of the mechanism of chemical reactions. We've got full orbitals reacting with empty orbitals. Yes, stuff in the middle can happen as well, like partially filled orbitals can react as well, but let's not worry about that right now. So full orbitals cannot react with full orbitals because again, they can only support two electrons in an orbital. So if you have two full ones, they can't interact, because that would be excessive electron repulsion, and we're always trying to minimize that. Similarly, like two empty orbitals cannot react with each other because they have no electrons, and so there's nothing to react. Because all of these reactions are just electrons, and it's really all we all we deal with in the entirety of chemistry, except for nuclear chemistry, because that's well why it's called what it's called. So, orbitals exist around atoms, and then when multiple orbitals on different atoms interact, they combine to form what's called molecular orbitals. And so how these come together is, you can think of is, so they can let's see, I'm going to do a bit of drawing. So I'm gonna say itchy eye. Sorry. Okay, so orbitals, so molecular orbitals, which is like orbitals that span more than one atom. Like take just simple hydrogen gas, for example. these just have these spherical orbitals. So these are just called 1s orbitals. So s orbitals are, well, the s is for spherical. And so there's a couple ways these can combine. There can be an in-phase reaction, which is like if both of these spheres of electron density, if these overlap, then they'll look like this. And so these are spherical around the hydrogen atoms, and when they're in phase, which say they're both of this one phase, then they will just kind of surround both of the hydrogen atoms, because think of it like, you know, those like really big bubbles that you could like if you take like a coat hanger, turn it into a circle and put it into some soapy water and just like make some big bubbles. You bring two of those together and they just kind of into one big bubble, and that's how these interact. So these are two little bubbles of electron density around each of these hydrogen atoms. So let's actually so if these are two individual hydrogen atoms, each of them has one electron. So that's a little dot beside them, and that electron resides in this spherical orbital. So you could, like, if we were to draw the orbital around each hydrogen atom, then this is what you'd get. But there's another way that these could interact, and that is if one of them is positive. So I'm just going to draw this above the hydrogen atom. So if one of these has a positive phase, and the other one has a negative phase, so we just kind of depict that by like shading one of the phases. So this one, let's call this one positive and this one negative. Again, it's not about charge. It's just saying this one is different from that one. They're opposites. So if these ones interact, then you get what's called an antibonding orbital. And so that's going to be here and here. So when you combine, when you have a molecular orbital that has these two different phases of electron density, it's no longer like a you know, two bubbles coming together and forming one big bubble. Think of this interaction as two balloons, like a blue balloon and a yellow balloon, and they can press up against each other, but they won't overlap. And so they want to keep their different phases of electron density separate from each other. They can't overlap with each other, because any overlap of these orbitals with opposite phase, just like up here, that results in destructive interference. And so if you add these two wave functions together that are equal but opposite in phase, then they cancel each other out to zero. And so they can't interact, because any interaction between these two just it cancels each other out, and then the electrons just can't exist in that space. So these two phases of the electron density stay completely separate from each other, and that forms this little line between the two of them, between these two phases, where you have zero electron density, and that's called a node. So when you so if you have an orbital like this one, a molecular orbital where two orbitals with the same phase have overlapped, then you've got this electron density across the entire bond, and so having that continuous that just like continue. Sorry, the line is called a node or no electron density. Same thing. So this kind of this separation between the two phases where there is zero electron density is called a node. And so yeah, a node describes a region of zero electron density. So yeah, if you have an overlap of orbitals and there is continuous electron density along the bond and like that is across the entire bond, that's called a bonding interaction. And so this is an interaction of electrons that holds these two atoms together. And so you might have heard these called like a covalent bond, and that's perfectly reasonable thing to call it. Because there's other kinds of bonds. There's ionic bonds as well, and different stuff like that. But those have a bit of a different nature. Don't worry about them right now. What we're concerned about right now is molecular orbitals, where this bond has this continuous electron density around it, and that holds these atoms together. Whereas this one, if you have a node that occurs along the bond, then this is called an antibonding interaction. And so if you have a case where so remember what I said, that orbitals can be filled or empty. And so if you fill a bonding orbital where like this is populated with electrons, that is it translates into a force that holds those atoms together. If you populate an antibonding orbital with electrons, that breaks a bond between these two. That actively tries to separate those two atoms. And we're going to see some examples of this. I'm not, for a change, I'm not just like getting distracted and talking about something else. This is actually very pertinent to what happens in substitution reactions. So basically just that you can have orbital interactions of the same phase that have this bonding interaction, and this interaction of opposite phases where you have an anti-bonding interaction. Like cell division, I'm trying to think if that's... I don't know if I want to say that it's parallel to cell division. Because like I'll have to think about that. I'm not going to endorse or deny that analogy at the moment. I need to spend some time thinking about that. Other forces being visually. Yeah, sure. Like that's fine. To make just like kind of this visual idea of like if you feel an antibonding orbital, then you know it's trying to pull these two apart. But even that breaks down if we have something like if we have a carbon-oxygen double bond. It's called a carbonyl, and so the lowest unoccupied molecular orbital is this antibonding orbital. So I think I'm filling this in and have your node. So if you populate this orbital, so if a full orbital comes and overlaps with this carbonyl, this antibonding orbital, if you fill this, you break a bond between the carbon and oxygen. But there's two bonds between the carbon and oxygen, so they don't actually separate the atoms. They get a little bit further apart. This bond lengthens, but it doesn't break. So like it kind of breaks down for anything but a single bond, but for that purpose, yeah, I think you could make that comparison. Hi. Okay. Um, was there something else? Because that just triggered a thought that I was. There might be more I need to talk about before I tackle this. But this is. I think we're okay. All right, so I'm going to take away the planetary model of the atom and the plum pudding because those are obsolete. We don't need them. Goodbye, Bohr. Okay. So. Okay, so that actually starts on a really complicated one, and I don't want to start there. Not really complicated like this. Yeah, it's not one I want to get into yet because we need to have some simpler problems to start with. So let's just start with something like this. Okay. So we've got this is just an alkyl halide. So I'm going to. So this has. Yeah. Go away. Carbon here. A couple hydrogens. And a bro. And so let's say we've got. So we got this. We need something like. This. Okay. So this is CH3CONA. So this is something that I've drawn wrong. Just a moment. Haha. Very good. CH3O. Na. Okay, so this is sodium methoxide. So it's basically a methanol that's been deprotonated. So it's got this negatively charged oxygen. Now there's a sodium here as well because we always have to have charge balance in anything that we're doing because we're not just going to have just unbalanced charges because that's not how nature works. So you can draw it out this way with the sodium plus and this H3CO minus. I'm going to ignore the sodium right now though, and the reason that I'm ignoring it is because it doesn't do anything in this reaction. It's just there to balance the negative charge of this sodium methoxide. So it's just called a spectator ion. So it has no involvement in the reaction. It's just there to provide charge balance. So I'm going to ignore it for now. So when we're doing nucleophilic substitution, there's a few things that we need. And I'm going to draw this out properly and put my lone pairs around because that's important. Okay. So nucleophilic substitution has it's a reaction between a nucleophile and an electrophile. And I'll explain what those are momentarily once I finish writing them. That's what I'm doing. Okay, so nucleophiles are species that have excess electron density. E. E minus being the just abbreviation for an electron. So excess E density. And electrophiles have how do I describe this? Probably should have planned that out. Because it's not an electron deficiency, have basically an electron file wants more electrons in it. And let me explain what I mean by that, because that's not a very good definition for what an electrophile is. So an electrophile is just a compound that has a region, or an atom that doesn't have as many electrons around it as it would like. So in the case of our alkyl halide here, bromine is more electronegative than carbon. So it pulls harder on electrons because it's trying to get them closer to itself. So it's got more more protons in it, and so it's going to have more of this like attraction for electrons. So that means in a bond like this, where the carbon is less electronegative, so it does not pull as hard on the electrons around it as a bromine does. So we've got. I wonder if I should. Yeah. So let's try this out. So in a molecule of bromine. Oops. Good lord. What do I do? Do. So this is just Br2. It's the elemental form of bromine, and so I'm just going to kind of sketch out. Here's like kind of like the electron cloud that is around bromine is equally distributed between these two bromines because there's no difference in electronegativity, so they're both pulling equally hard on the electrons around them, and so the kind of like the electron clouds around them are equal to each other. There's no preference for one or the other. But in something like in a bond like this, where bromine has a higher electron density than carbon, or sorry, a higher electronegativity than carbon. So again, that means like it is pulling on the electrons around it harder than the carbon is. So you're going to have like a large lobe electron density around the bromine and a small one around the carbon. This is certainly exaggerated, but just to show like that electron density that was equal around the bromines is not equal when it is in a bond with an atom that's less electronegative than it. So carbon is less electronegative. So it kind of like gives up a little bit of its electron density to the bromine, because the bromine's pulling very hard on these electrons. And so what that does is it induces a partial positive charge on the carbon, right? Because so the carbon has a certain electron density around it that makes it neutral, that offsets the charge from its protons in the nucleus. But if it's around another atom like bromine that's pulling its electron density away from it, now it's got the same amount of protons, but now it has less electron density around it, and not enough for us to call it like a fully positive charge, but it skews the electron density towards the bromine. Or the chemistry way of saying that is that this bond is polarized towards bromine. So it's a polar bond is one that has like different regions of electron density. So this one has a slightly positive charge on the carbon, and a slightly negative charge on the bromine because they're pulling on the electrons around them with different strengths. So in this molecule, carbon is serving as an electrophile because it's got that partially positive charge because it's connected to the bromine. So this is our electrophile, is this here. Whew, that was a lot of talking. Okay. So this carbon that is attached to this more electronegative atom is an electrophile. And that's pretty broadly true of lots of different compounds. Sorry, I got distracted by music and it was delightful. So yeah, like this carbon here would be an electrophile. This carbon here would be an electrophile because they're connected to bromines. This carbon is not an electrophile because it's only connected to other carbons and hydrogens, which are very close to it in electronegativity. So there's no, these are not polar bonds, and you can't have a particular. Well, I want to be careful how I say this. So generally, in any kind of carbon-based chemistry, you have to have a polar bond in order to have this nucleophile, electrophile kind of labels. So we've got an electrophile in these two molecules. But now to do a nucleophilic substitution, we need a nucleophile as well, and that's an atom that has kind of excess electron density around it. So you could say the bromine is a nucleophile here, which is not super wrong, but it's not really right because it's a very, very small excess of electron density. So bromine's a pretty bad nucleophile, but we'll get into why at some point, but not right now. Because right now I want to talk about this system where the most nucleophilic atom here is this oxygen. It's got 1 bond and 3 electron pairs, so it has a negative charge on it. And so it's got more electrons than it normally would around it. So it has this excess electron density. And so this oxygen can use one of the lone pairs around it to attack this area of lower electron density, the electrophile. And so if we now, I'm going to take out those other arrows because they're just kind of in the way. So the way that we shuffle electrons around in chemistry reactions is that we draw an arrow starting from one of the lone pairs, and it points at its target, at the electrophile here. And so when it does that, so this is a filled orbital on this oxygen interacting with an empty orbital between this carbon and bromine that looks a lot like this. But sorry, looks a lot like this. So this is the lowest unoccupied orbital that is around the carbon and the bromine, and it is an anti-bonding orbital. And so when the lone pair from oxygen comes and interacts with this orbital, so it's a filled orbital interacting with an empty one, so it fills this antibonding orbital and breaks the carbon-bromine bond. And so when this happens, so you can't have more than 8 electrons around a carbon at any given time. So when we form a bond by using this electron pair from the oxygen to form a bond with the carbon, it must break one of the other bonds around the carbon, and it can do so with this carbon-bromine bond. And that, so the product of this, okay, so these are the products of this reaction. So you have this oxygen forms a bond with the carbon here and kicks off the bromine. And this is like for a couple reasons. So it fills this antibonding orbital, breaks that bond, which is good because we cannot have 5 bonds to carbon. That would break the octet rule, and it's not allowed for things like carbon. And it kicks off this Br minus. And a Br minus is pretty stable because yes, it's got a negative charge, which is not super favorable. But this negative charge, or these extra electrons around it, are in a very, very large orbital, because bromine is down in like the 4th row. Yeah, fluorine is 2nd, chlorine is 3rd, bromine is, so yeah, the 4th row element. So very large orbitals around the bromine. So that negative charge is not ideal. We don't love it, but it's very spread out. And one of my professors always like to repeat often that nature abhors a focused charge. So the more that we can spread out charges, the happier they'll be. And bromine does that very well because it's just a very big atom. So that negative charge is very diffuse. Yeah, and so by doing this, we've removed a negative charge on oxygen, which is very small. It's a very, very small atom. And so we've taken that negative charge and spread it out over a much larger area, which is very favorable. And so, without getting like too technical about the reasons that that's favorable, like it goes from a more focused charge to a less focused charge, and that's a favorable thing. So this is then a reaction that works, and so this is called an SN2 reaction. And the reason it's called SN2 is because so the 2 refers to the number of molecules that are interacting in the rate determining step. Rate determining step is something I will talk about at another time, but it's essentially, if you have a series of steps, it's the slowest one. And it's the kind of bottleneck of the overall reaction. But in this case, there's only one step to this reaction, so the only step is the rate determining step, and there's 2 molecules that interact in that step. So that's what the 2 is signifying. N is for nucleophilic, S is for substitution, because we've substituted one group for another, and it happened because a nucleophile attacked an electrophile. And oh boy, if you're still with me after all that, frankly, wow, because I feel like I'm barely with me after all of that talking, and I need to drink some water. had to get a charger to try to rewatch the segment. No worries at all. Yeah, it'll be up on YouTube shortly after the stream is done. Um, whew, yeah, it's a lot to tackle. I was for whatever reason I was thinking like this wouldn't be as much to go over in order to get to the reactions as I was as it turned out to be. But is a slow step slow for the same reason ground state takes longer to go to like position 3? I need to think about that question for a moment. No, it's not the same. It's not the same as that process. So that process we're talking about is like going from ground state to an excited state, and so that is like when it's staying bound to the same atom, but you're just so you have photon coming in that hits this electron, and it absorbs that energy and is excited into a higher energy state. So that's what that thing is that you're referring to, and but this is getting over this activation energy. Let me draw that in a less dumb way. So this is, yeah, this whole molecule, essentially, or at least the reactive site, the reactive atoms in these molecules, are being how do I explain the difference between these? Okay, so think of it this way. So this situation here, we're talking about like I'm going to borrow from that slightly obsolete but still kind of useful Bohr model of the atom. Yes, exactly. So the slow step is is a step that has the largest activation energy. So I'll draw another example of that in a minute to nail down this distinction. But for now, so this situation here is like going from, like, if this is the ground state. So this is. So that's what we're talking about here, and then do. So it's kind of like this. So if this is the ground state where this electron is in the lowest lying orbital that it can be, then this process is exciting it into a higher energy orbital. And yes, I borrowed from the Bohr that Bohr model of the atom that I said was wrong, and it is, but it's kind of useful in talking about this effect, this phenomenon, because this is like the Bohr model is what they used when they were talking about like when they first articulated what's going on with this. So it's yes, like this is that process that we were talking about. But yeah, so this is, so let's call this once again. So this is the reaction curve of an SN2 reaction, but there's different ones. So like, I think next stream we'll talk a bit about SN1 reactions. And those reactions follow a different path. So if this is your starting point, then you've got a big activation curve here. Activation energy there, I should say. and then you've got a smaller one. So this is an SN1 reaction is a two-step reaction. But this one, the first step here has a really large activation energy, and the second step has an activation energy from here to here. So this is step 2 is just that large, and step 1 is this really large activation energy. And so the first step here is the rate determining step because it has that very large activation energy, and that's what determines the kind of the speed of the reaction as well. Yes, exactly this. So yeah, there's yeah. So I think I could quickly go over one. Missed most of the explanation earlier, so maybe from a little up. That's totally fair. Yeah, if you go back and watch this, hopefully it makes a bit more sense. Because like I feel like my explanation of the kind of the theory that underpins this, it was kind of inadequate because because I didn't want to spend about 5 or 6 hours explaining like all the different concepts that we need to do these reactions. So yeah, hopefully it helps to go over that stuff a bit. If not, come armed with questions next time, and we can definitely get into the meat of this. But yeah, so the I can't remember what I was about to say, but that is probably an indication that I am my brain is starting to fizzle a little bit tonight. Yeah, so I think I should probably wrap this up fairly quickly here, but yeah, hopefully that helps like kind of make the distinction between these two kind of processes, because like here you got reactants over here and you got products over here, and so this is interactions between molecules that like this whole energy this whole system goes through these energy changes as these different molecules interact and make new products that have different energies in their bonds, and again, it's all just like a measure of how how spread out are the electrons, like how much have we change the electron repulsion, because that is like 98% of all chemistry, is how efficiently can we spread out the electrons and reduce the amount of repulsion between them. All right. Okay. Whew. All right. So, yeah, I just doing a little self-check-in, and I think I am more or less completely fried here. Oh, I just realized I ignored Tian's comment about, yeah, that went into a lot of different OChem stuff. Yeah, turns out it's a really big subject, and yeah, like this is kind of the how a chemistry curriculum goes, is that like pretty much everything that you get into builds on something from that you've learned previously, and so like this is this is why I get into saying things like memorization isn't super helpful. Like you have to have a process to go through so that you can understand the material better. Yeah, and so like kind of the running joke in chemistry is that every semester they'll lie to you a little bit less. which isn't exactly the way I prefer to look at it, but it's sort of kind of true. We get a little closer to the truth by like kind of having this this educational scaffolding that like we build this up by simplifying this so we can understand what happens and why it happens, and then we can get into the more intense discussion of how this happens. um, and that's the harder part that we build up to eventually. And then we get into quantum chemistry and really scar you for life. I'm not bitter or anything, but that's fine. Yeah, so I think that is about all that my brain can handle for today. Hopefully yours is doing okay. But yeah, I will be back on Tuesday, and we'll keep going over a bit of this. Yeah, I figure I need to do some more thinking about what has to like what I need to go over to hopefully make this as doable as possible. But in the meantime, I hope you have a lovely weekend. I will see you on Tuesday. Thank you so much for coming and hanging out. Appreciate you, and you take care of yourself. Okay, bye.